mesh addressing header. So as we talked about last time, that when you have a mesh network, you have 4 addresses: source, destination, and intermediate where it is going right now on this hop. So if you're going from the source to P1 to P2 to P3 to final, when it is between P1 and P2, this will transmit that please P2 pick it up. So it will put the destination address of P2 there, right? So the question is, if P2 is the destination address, what happens to the final? Where do we put that? And so basically IPv6 needs a place to hide the final address and get it back. Same thing for the originator. Here the source address would be P1. So what do we do with the originator? So there is additional header which is added to the IPv6 at every hop. And so that header will have the original address and the final address, and it will have how many hops are left, and then 2 more bits, V and F. F will tell whether it is a 16-bit address or a 64-bit address, and V will tell the same thing for the source, whether it is 16-bit or 64-bit. Okay? So this header, now here is one more thing, is that every header option has a dispatch byte which tells what kind of header this is. So this dispatch byte is numbered, it turns out it is numbered 10 in hex, or if you wanted to convert it totally into decimal, that would be 32, if I am right, 32, is it? 16, 32, 16. That would be 16. So generally we write in hex anyway. So this is 10. So if the dispatch byte is 10, yeah, it says right here. If the dispatch byte is 10, then this is a mesh addressing header. And mesh addressing header, all it does is has the addresses and Y hops left, so that basically now you know that it is not recirculating in the no cycles there. And so you start that we are going to go 3 hops, and at every hop the number will be decremented, and then when it becomes 0, the packet will be thrown away if it is not already at the final destination. Okay? Yeah.
So what is the 1 0 between the B and the dispatch byte?
You're right. That's a mistake. Yeah, that's the mistake. So we need only 1 0, so this 10 goes away. Okay? All right, broadcast. So broadcast, when you have broadcast, then all you need is the dispatch byte to be 50, that, and then a sequence number is added. So because what happens with the broadcast is you have to send it to your neighbor, and they have to send to their neighbor and send to their neighbor. You don't want things to come back and then go again and again same place. So you put a sequence number, so that way you know that this sequence number I've already broadcasted, I'm not going to broadcast it again, and I'm not going to forward it again. Okay? So that there is no address required, nothing required, because it is going to everyone. Fragment header. Now there will be a lot of fragments. Why a lot of fragments? Why there would be a lot of fragments? Anybody?
Because the IPv6 had to break into small fragments.
Yeah, because IPv6 is so big and 15.4 is so little, there is no way you can send IPv6 into one frame at all. There is no way, right? And so there are a lot of fragments, and so the fragments have to be basically have a number. The dispatch byte is 1100. No, this is not the dispatch byte. This is the dispatch byte is 1, 1. So dispatch byte is not shown here. But after the dispatch byte, the first 5 bits, if they are this value, then that is the first fragment. If it is this value, then it is second, third, fourth, fifth, sixth, nth fragment. All right. So this 1 bit there indicates whether it is the first, whether it is not the first. Actually, 0 means first. All right, and 1 means not the first. So once you have that, then you put the IP packet size, the datagram tag, and then payload. Datagram tag and datagram offset. So what is the? So let's just discuss those two. So full packet size. Okay, there might be another error here. Full packet size in the first fragment, so it may not be here in the second one. Okay, and then you have datagram tag with sender and destination MAC addresses. Okay, so you have that, and then fragment offset. What is a fragment offset, or actually datagram offset? Fragment offset is when you break something in, you want to know which place this fragment belongs. So offset is just from the beginning of the packet to that point. Okay, that length in multiples of 8 bytes. So whatever the number of bytes before that fragment is, you divide that by 8. Whatever number you get, that is the number you put in the fragment offset, datagram offset. All right. Why divide by 8? So that you just use 3 less bits. That's the only reason, because if you were to put all the numbers, then you will need 3 more bits. By dividing by 8, and then you just have to keep multiple of 8, which generally is already the case. And then the payload, as usual, we don't compress the payload. So what we have compressed so far is basically the the headers and the fragments and things like that, right? So the first packet will have a different bit and the packet size and a tag, which is the number. Now, basically, this is the tag, which is 16-bit. It indicates that these are all the same packet. So they are somehow derived from the source and destination MAC address, because both of them could be very long. Either both of them could be 16-bit or could be 64-bit, or could be 48-bit, whatever. So the idea is that somehow you derive 16 bits. So this is like a packet number, and then all of them will have 1111 or 3030, whatever number that is, and so you assemble all of them into one packet, one IPv6 packet. All right, and the fragment offset helps you put the right place this payload. Okay, this is very similar to the fragmentation in IP. If they taught you fragmentation in IP, which they should have in 473, this is exactly how you do the fragment and the fragment offset. Now, so as you can see, notice here, basically every bit is very expensive, and so they are trying to reduce the number of bits as much as they can. So the next thing they need to reduce is the addresses. So before we reduce the address, let's understand the address format. So Ethernet had 48-bit, we already talked about, right? 48 bits are done as follows. First bit is called unicast, multicast. Top value is 0, bottom value is 1. If the first bit is 0, that means it is the Ethernet address is what? Unicast address. If the first bit is 1, it's a multicast address. And therefore, most of the devices that you have, Ethernet devices, they don't look at the whole address, they look at the first bit. If it is 1, then they just pick it up, regardless of what multicast address it is. Whether we are listening to that multicast or not is decided later. Okay? You just pick up a multicast, and then you look through the table of multicast addresses that you are looking at, and if it matches, you keep it, otherwise you throw it away. If the first bit is 0, then it's the unicast address, and right away you match all 47 bits left in hardware, basically. So there is no table. Just you look up in a memory into it, what they call content at the scam, and then you pick it up. Okay, so the first bit is very important. It is universal or multicast. Second bit is actually unicast and multicast. Second bit is universal or local. Now this is really interesting because they use the word universal. You know what is the difference between global and universal? Anybody? Does anybody know the difference between global and universal? How big is the globe and how big is the universe? Globe is so small. Universe is so big, right? So this is a universal address. Remember, if you go on the sun, it will be unique. And they are going on the sun right now, actually. So NASA has this solar network. So they will use universal unique address, right? So this is universal or local. So just like, basically at that time when we were designing Ethernet in 1978, there were two camps. One camp said that I want to address it by the building number and the room number and so on and so forth. And other people said, no, we want universally unique. Both camps won by having one bit which tells you which one it is. It turns out after that nobody has used your local yet, or it is not used much. So universal is finally won after so many years, but at that time it was not clear. So anyway, universal or local. But the only mistake they made was that they selected U equal to 0 and L equal to 1. If it is 1, then it is local. If it is universal, it is 0. And then 22-bit is the manufacturer, and that is called OUI. OUI, IOU, or something like that, OUI is organizationally unique ID, simple thing for company ID. Okay, so if I look at your computer and find out your MAC address, I can tell you who made that chip. Whether Intel made it, AMD made it, Cisco made it, by looking at those 22 bits. There is a table on the internet where you can go and figure out the whole thing about the OUI. And then 24 bits are basically assigned by the company. 15.4 went further ahead and made it 64-bit, and they call it Extended Unique ID, EUI. Everything else is as before. First bit is universal, multicast, universal local, unicast, multicast, universal local. 22-bit of OUI, but then there are 40 bits instead of 24 bits, 16 more bits from the company. What happened? 64-bit, okay. All right, so this is what is called EUI. And actually, to be exact, it is called EUI 64. EUI 64 because it is 64-bit, and EUI because it is extended unique ID. All right. Now, I just mentioned that this is a universal local. This was a mistake. Actually, it turns out, the broadcast address. What is the all broadcast address for Ethernet? All ones. So there, first bit is multicast, which is good. The second bit should be what? Should be 0 if it is to be universally unique multicast address, right? But it turns out that broadcast address would be classified as local by that bit interpretation, but that's an exception. So they made an exception that if it is all ones, it is unique, globally unique broadcast, period, done. So it's not a local address, but it's one, but it's universal. Anyway, so the reason I have to bring that up is because this is IETF is trying to fix that part. So the local one was incorrectly assigned by the original people. So now IETF wants to relabel these bits, and they want to call it 1 if it is local, 0 if it is universal, because most of the time it will be 0. Nobody uses local addresses. If there are zeros, we can get rid of them very fast. Right? So when you're thinking about compression, when you're thinking about smaller things, it's better to have zeros than ones. If nobody is using that local addresses, so we call them 1. But all broadcast addresses are 1. Okay, so that's the mistake. Now the thing is, IETF 4291 changed the meaning so that L equal to 0 means local, and the second bit is called universal bit. Okay, you name it universal. The bits are called by their whatever the 1 means. So this is a multicast bit. This is now a universal bit if you follow 4291. And So if you write an address in U-bit formatted UI64, EUI64, then you will take EUI64, flip the second bit, and that would be called U-bit formatted EUI64. That would be called RFC 4291 format. Okay? So, having done that, now we can take these 64 bits and put them into this format. Now, who can read this double colon? What does that mean? Anybody who knows that? What does double colon mean? Yeah.
I think it means the rest of the octets are 0 or 1.
Zeros, okay, good. So the rest of the people didn't know that? I should probably sit down with 473 people and make sure that they teach all this, because I mean, this is 1991, way beyond my reach. I mean, like 20 years old stuff. And if people don't learn it now, and then they will be in trouble. Anyway, so this is IPv6 notation for addressing. Is that since the addresses are so big, and most of it is 0 anyway, so they don't want to write zeros, so they write 2 colons. 2 colons means fill up as many zeros as you need. So here FE0 is 1 byte, 2 bytes, right? And this one is 64 bits, 8 bytes. Total we have 10 bytes, and we need 16. So we put 6 bytes of zeros there. Okay? If you were to expand this, you will write, so now we are writing 2 bytes at a time, right? So you write FE80 colon 00. Okay, I mean, you can either write 8 zeros if you're writing in binary, or you could write 2 zeros if you're writing in hex. So 00 colon 00 colon 00 colon, well, actually 4 zeros will make 2 bytes, right? Because each thing is a nibble. So you write 4 zeros colon 4 zeros colon 4 zeros colon, you write it 3 times, that will make it 6 bytes. Okay, so, and that address is called link local. Again, this is IPv6 concept, and we teach, I mean, I taught all this in 1991. Believe it or not, I taught it not 91. I taught it in 1994 when I taught my first IPv6 class, and I have taught it in every every 473. But a lot of people are coming up here without any knowledge of IPv6, which is really pathetic. But link local means that this address is good only on the link inside the house. Just like 16-bit addresses, link local addresses are inside the house, and so you don't need DSCP. You can make up your own address and be in business right away. All right, this is called auto configuration in IPv6. So any device who knows its UI, which is built into the hardware anyway, can make its IPv6 address like this. It will just put FE80 in front of it, put 6 zeros, and then put its 64-bit address. Now it says this is my IP address, and it can start talking to everybody. The only difficulty is that it cannot talk to anybody outside, because this is link local. This is not global address. Somebody else might have the same address. Actually, they will not have it because they will not have the same EUI64. But link local addresses are not supposed to, they are just like private addresses. Okay? So you cannot get out. If you want to get out, you need to get a global address, and then so for that you do have to go to somebody and find out what is my network prefix. And the network prefix actually in IPv6 is the first 8 bytes, 64-bit. If you get that and then you put whatever you want to put after those 64-bit, that would be globally unique because that network is only here, nowhere else in the world. Okay? So this is link local address. So you get a link local address from your EUI 64-bit address. Again, one more time. How do you get it? First thing you do is you flip a bit. Which bit? The second bit. And once you flip that bit, then you add 6 zeros in the front, and then you add FE80 in the front. I shouldn't say 80, FE80, because it's all hex. Okay? All right. So I gave an example here. Suppose your link local address, so suppose your EI64 address is 40, and I'm kind of misusing this double colon here because EUI doesn't use double colons. But since it is so long, I don't want to write too many zeros. So 40 is, sorry, not 40, 40 is this 40:01. Right? If I U-bit format it, I will flip the second bit. So I will get 0::1. Now how many things I am skipping here? Tell me. How many zeros am I skipping? For 64-bit, how many bytes do I need? 8. How many do I have? 2 bytes. 4 nibbles, 2 bytes. So I am skipping 6 zeros in the middle. Okay? So imagine that you have all those 6 zeros in the middle. This is your U-bit format addresses, and then you make it your link local address by putting 6 more zeros in the front, and then F and E, 8 and 0. All right. So now you understand how you can get an IPv6 address without going through a DHCP server. You see, on IPv4, you cannot do this. You cannot just make up your address and start talking, because somebody else has already decided what the network is and what the service mask is and all that. So you have to get it from somebody. So you have to go to DHCP. And this was one of the features of IPv6, which was advertised right at the beginning, that this is a good thing that we just plug and play. All right. IEEE 15.4 allows you to have 16-bit sort addresses, and each PAN has a 16-bit PAN ID. Okay, so you have 64-bit address yourself, and you are part of a home or a network that has 16-bit address itself. Okay. So you don't use 64-bit, but you're going to use 16-bit of yourself and then 16-bit of the home address, PAN ID. 1 bit of the sort address and the PAN ID is unicast multicast. Now PAN ID is very similar to the other addresses we have seen. The first bit will indicate it is unicast or multicast. Second bit will indicate whether it is universal or local. And if you put all ones, that means broadcast. That means I want to broadcast it to all the networks that I can reach. All the PANs, not just, okay. If you put that PAN ID fixed, not all ones, but you put all ones for the host part, then you want to broadcast to all the hosts of this PAN. So broadcast is of 2 types, right? In PAN broadcast, out of PAN broadcast. In PAN broadcast, you have a fixed PAN ID, but the host address, destination address is all ones. Out of PAN is what? The PAN itself is 111111. So now you will form an IPv6 address by putting FE80 and putting lot more colons, lot more zeros, then PAN ID and sort address. If you don't know the PAN ID, just use zeros, because we love zeros. So anyway, put zeros, and then at the end you have a sort address. Second bit of the PAN ID will always be 0, since it is always local, and the second most significant bit. Now here you think, when I was reading about this, a lot of people are confused. about this bit sequence, and I wrote a whole book on FDDI, which was the 100 megabit Ethernet. So I know exactly. So basically, how do you count the bits? Lot of people put 6th bit, and they're counting from the right. You don't count from the right, you count from the left. So you always have to count from the most significant bit. Okay, so when we say 0th bit, we mean the most significant bit. When we say first bit, that is the second, and so on and so forth. So 0, 1, 2, all the way to 31, right? So second most significant, here I don't mean number 2, it is second most is basically, if you were to level from 0, that will be bit number 1. So second most significant bit should always be 0, because that is what indicates local or universal. It's really strange. I was just thinking about this global versus universal. IP doesn't use the word universal. IP uses the word global. Okay, Ethernet uses universal. So Ethernet is, and I think basically because IP was designed first, they didn't think of going universally. So they were thinking globally. But Ethernet came later and they thought universally, right? So that's why. But they are basically same meaning right now. It doesn't really make a difference whether it's global or universal. But it's just interesting to know that the words are different. All right. So now you know 2 ways to make the IPv6 addresses. One is if you know the complete 64-bit, then you do that. If you use 16-bit short addresses, then you know how to do that too. Right? So either from your pet name, which is your home name, 16-bit address, you can make the whole address, or from your unique name, full name, you can make the whole address. So now that we can use the addresses, the next thing is how do we compress these bits? And the reason I wanted to take you through this compression process is I could have just said the header is compressed and be done with it, is because this is the kind of a scheme which is used at many other places. Not the same scheme, but there are other compression header things. Anytime the bits are expensive, you have to compress the header. And so these are the kinds of the tricks people play. So this is called HC1. First I'm going to talk about this stateless compression, which is called SC1, SC2. The second one, which we'll talk later, is called context-based compression, which is called HC actually, IPSC. But this is stateless because nothing has to be remembered. Everything, all the information is in the packet. In the second one, something has to be kept in the memory. So in this one, first of all, we remove the IP version field. So we are done forever. We don't need to know that this is IPv6. It is IPv6. Right? When IPv7 comes, then we'll have to worry about it. But right now, there is nothing. So that is not sent. And if you look at the packet on the wire, or actually wireless, you will not see the IP version field. That saves you some bits. Then flow level field is removed if it is 0. Now flow level field, again, if you know IPv6, you know that there is a field called flow level, which tells you what flow number it is, and that is generally not used, so it is 0. So we just don't send that 16-bit field actually, and we put C equal to 1. C is this bit. If this bit is 1, means we have removed the flow level. If it is 0, then find the flow level at its right place. So now we saved 15 bits at least, right? And then UDP port is 16-bit. Instead of 16-bit, we just send 4 bits. So we save, well, not fully 12, but let me show you in a minute. So what we do is we put the port number, use the port numbers which start with F0 in hex, or start 61,616 to 61,131. In that range we use the port numbers. So we only need, so this is actually total is 16-bit port number. Instead of that, we just have 8 bits. 8 bits are always F0 and we don't have to send it. Okay? And let me just double check here. So this is 131 minus 611. So this is lower. this is lower, and so something is wrong with these numbers. F0XX, one can calculate what the first number would be and what the last number would be. The main mistake that I am seeing here is that it says 4-bit ports are sent, but I am seeing here 8 bits left. So they have to have 12 bits in common. So just assume that basically there are 12 bits in common and 4 bits are the only one, and so you just use 16 ports. So 4-bit ports are sent and the UDP length field is omitted. Why we omit the length field in UDP? How do you know the length if you just remove it? Is because the length might come in the Ethernet packet, or actually Ethernet doesn't have a length either. It just be figured out from the Ethernet packet itself, because if Ethernet packet length is wrong, well, Ethernet or 15.4 or IP, whatever it is, the checksum will not match, so we know the length is always correct. So we remove that length field, we remove the port numbers, most of it, and we remove the full flow ID. So if you do that, then the HC1 header, the first part of the header will look like this. The dispatch field would be this bit pattern, and you don't have to remember the bit pattern. I just have to know that there is a dispatch field which is different for different kinds of these options. And then you have source address encoding. Okay, and the source address encoding is 2 bits. If it is 01 means I have not compressed that. If it is 00, it's not compressed. If 01, then prefix is not compressed, but the ID is compressed. So let me tell you what is prefix, what is IID. IPv6 addresses are 128-bit long. The first 64-bit are called network what? I just mentioned that a few minutes ago. First 64-bit are network. Anybody remembers what was that? Network prefix. Okay. The last 64-bit are the interface ID. So you can compress either part. Okay. Prefix ID is much easier to compress because if you are not going out of the house, we know your prefix. Right? So these 2 bits 00 will indicate whether both are uncompressed, 01 will indicate that only IID is compressed, and 10 will indicate that compressed means omitted here. Okay, that the prefix is omitted, and then in this case both are omitted. Now when they are omitted, how do you find them back? Well, you can derive it from L2. What is L2 here? L2 is 15.4. You look at the 15.4 address, because everything which comes on IPv6 goes down to IPv4. You look at that, and that is what you put it back into the IP field. So you can derive it from IPv4. Derive it from 15.4. All right. So this way you can compress, and this same definition actually is applied to source and destination. There is a little bit more complication which I am not going to go. But if you have to ever use this stuff or write a program to do this stuff, you should go to the RFC and read it, particularly for the multicast. So this is just for unicast. All right. Now, so we already know what is C bit, and now we need to know NH. NH is the next header. If it is 00, that means the next header is not compressed. Inline means it is not compressed. If it is 01, then the next header is 17 UDP, which means the next header is UDP, and now we have to do something for UDP because we can compress UDP. 10, the next header is ICMP, and 11 means next header is TCP. Okay, so now the next header field in IPv6 is, I think, already 8 bits long. I could be wrong on that one, but 8 bits long. So now it is only 2 bits we use, and we don't have to put next header type in all 16-bit, we just have to put 2 bits. If it is 01, we know it is, because these are the most common protocols that we use on IPv6. Now, if you had a protocol which is not one of these, what do? First line, use 00. 00 means find the exact protocol type at the right place where it is supposed to be. I haven't changed it. Alright, but most of the time it will be one of these three, and then we have compressed it. Okay, NH. This is a 0, no problem. This is S bit. This says that the UDP source port is in the range that you want. And this one says the destination port is in the range that you want. And so therefore, we are going to use only 4 bits there. L bits means that we have removed the length. And everything else is same. Now this part of the header is called HC2, header compression part 2, and this is called header compression part 1. Part 2 has to do with the next header. Basically, if the next header is 0, 1, 1, 0 or 1, 1, then all of this makes sense. If the next header is 0, 0, then you get the whole thing uncompressed anyway. Don't worry about it. So, the purpose of this to show you, now there is a contradiction here in my own mind here, that these are little devices, you want them to be simple, and you have all these rules, and they are doing all this calculation. So I am not sure whether this is worth doing all the calculation myself. I haven't implemented it, so I don't know. But maybe people have implemented it, they find this is better than sending the whole thing, which is a lot of bits there, right? So you are saving some bits, but basically that's what it is that by everything you compress and you do this and that, and it becomes. And this is actually a debate which I have seen many times, is that here the debate which I said, now that I talk about it, let me bring it up. Should any field be variable length? Because if it is variable length, it has to be handled by software. Hardware find difficulty handling variable length things. If it is fixed length, everything appears at the right place, you give the whole packet to the hardware and they just handle it bit by bit, and they do whatever they need to do. Hardware can handle fixed size, fixed place, fixed position bits very easily. Right? If it is variable size and if then else and this and that and this and that, then it is basically we are writing a program. It is very difficult to write a program in hardware. You can, but not the best thing. So this is what it is. This is if then else, and this is because we have very simple devices. They are supposed to be very simple and very cheap, so they are writing the software. Okay, so we are trying to save every 1 bit here and there. Then they said we can do even better, and that is called context-based compression. If we can memorize something, and so the problem with the SC1, by the way, was it works only with linked local addresses. You see, if it is only linked local, then only we can prefix, we can remove the prefix, etc., etc. If it is going outside, then it is very difficult to use that. So they said, why don't we just do something different? So globally routable IPv6 addresses which have different network prefix, and so they have a new compression which is actually called IPHC, and I don't know why this is called IPSC. It's basically IP is Internet Protocol, SC is header compression. IPSC, and it uses dispatch code bit and its own 13-bit base header. Okay, if you go back, I think somewhere I showed you the IPv6. Probably I removed that slide. Okay, let's forget about the base for the minute. So we have a base header in the IPv6 header. Okay. So basically, the first 3 bits, if it is context-based compression, then the first bit will be 0, 1, 1, then TF, and then NH. Now TF, I should have drawn a line from there to here. So this is the TF. You just draw a line from there to here, this table. Okay? There are 2 bits. If there are 0, 0, that means that the ECN bit has been removed, DSCP bit has been removed. Sorry, not removed. 4-bit padding is there, and the flow level is not removed. So now what is ECN bit? ECN is what is ECN? Anybody know the ECN bits? Congestion notification, explicit congestion notification. This is actually there in IPv4 as well. DSCP is differentiated services control point, right? And then 4-bit pad, and then flow level is another 16 bits. So the total is 4 bytes. So this is ECN is I think 2 bits, DSCP is 6 bits, 8 plus 4, 12 plus 16. Eight plus 8 plus 2, 24, 4-bit pad. ECN DSCP plus 4-bit pad plus flow label. Anyway, somehow they make up 4 bytes. I am just adding up 3.5 bytes because this is 2 bytes, 4, 4.5 bytes. So whatever, basically if it is 0, 0, then everything is as it is. If it is 0, 1, then DSCP is omitted. Okay, if it is 1, 0, then the flow level is omitted. If it is 1, 1, then all 3 are omitted. Okay. So depending upon this coding, we would have omitted one of those 3 fields: ECN, DSCP, and flow level. And again, you don't have to remember exactly what is the code points are, because that is not the purpose of this course. It's just that you have to know that those things are omittable. I mean, there is a way to omit DSCP or TF or DSCP or flow level and all that. So you should know flow levels, because if you don't know flow level, then I think you don't know much about IPv6 if you don't know ECN and DSCP. Those things you have to remember. But the code point 01 is this and 010 is that I don't remember, and that you don't need to remember either. Alright, so having said that, we know TF. NH is 1 bit, which simply means this, that the next header uses low pan NSC. So next header uses another compression, and I'm going to explain that in a minute. The second 2 bits are hop count, which basically means that the hop count is 1 or 64 or 255, because this is the most common value of the hop count. If it is one of those, instead of having 8-bit hop count, we just use 2-bit hop count. We are saving 6 bits. Alright, if it is not one of those 3, then we use 00, which means now we have 00 plus 8-bit. So we are going to pay the cost of 2 bits if it is not one of those, but luckily that doesn't happen, because most of the time it is one of those 3. Alright, then CID bit is used here. In a minute I am going to show you context ID. SAC, actually this might be in the next slide. Source address context, and source address SAM is, so basically we have 1 bit of source address context and 1 and 2 bits of source address, whatever that M stands for. So anyway, M is for multicast, and the same thing for destination address context and destination address DAM, whatever that DAM is. And then this is the ID, context ID, SCI and DCI. So how do we use all of this? Basically you take the SAC, which is 1 bit, and you take the SAM, which is 2 bits, total 3 bits. There is 8 entry table here, and the first combination says no compression. The second combination says we have omitted the first 64 bit of the addresses, so the only 64 bits are there. Third combination says we have removed the first 112 bits, so only 16 bits are left. The third combination says we have removed all 128 bit, get it from L2. The third says so on and so forth. Alright, so the idea is that by using just 3 bits we can remove 128 bit if necessary, if possible. and then this is 4 bits is actually the context ID, which is a table which will be basically 16-bit long. 4 bits will have 16 entry table, and this is the index into that table, and that table will tell you where to look for the source address if it is compressed. Then basically, so this first we need CID bit to be 1. If CID bit is 1, then we use these 4 and this SCI to look into the table to find it, and we use DCI to look into the table to find it, and so whatever is not omitted can be found in the table, but if these bits are set. Right? Sorry, it is a little bit complicated stuff here, but all it is that we are trying to squeeze every bit out of here.
So the dispatch byte, which was there in the earlier compression,
is not shown actually.
Not shown, and it mentioned something about dispatch code bit. So is it a?
So basically, what it is that this is dispatch is shown here, right?
So this is a byte till now, but that one was mentioning a bit. Dispatch code bit is
011010. Dispatch code bit. Let me figure that out, and I will probably tell you next class maybe. Actually, there are several questions here that I think there was another question here in the previous slide. Somewhere I had a 4-bit thing, right? This 4-bit XX. Yeah. And then this question of dispatch bits and bytes. All right. Anyway, it's complicated stuff, and in fact, here's in this book, the book. So there are 2 places that I found information good. This book has a good description, but it had an error because by the time they copied all these tables, some of the entries were wrong. So these entries are from actually if you go to the book, I think they have 010010 twice. So the best place to go is the RFC. And I can go back to the RFC and then check where the information is correct. All right, moving on. So if the next header uses low pan SNSC, so now there was a bit here which says that this is where is the next header? NH. Next header uses low pan NSC. This is the name of the compression. And so if that uses that, then the next header will be like this. It would be first 4-bit will be 1110. The next 3 bits would be extension header ID. So it will be one of these 3 things, one of these 8 things. And then the next header will be again whether it's 0 or compressed, and then you will have uncompressed field. Now if it is UDP compressed, if it is next header is UDP, then we can compress it even more. If it is something else, then we cannot compress it. But if it is UDP, then we can compress the port numbers. And so what we do is this is the first bit pattern. Then we have a C bit which indicates whether the checksum has been removed, and there are 2 P bits which indicate whether we have put how much of the port number we have put. We have put all 16 bits. We have put only last 8 bits. We have put last 8 bit of source, last 8 bit of destination, and the 4 bits of destination and source. So actually that makes more sense. So basically this 4-bit answer I think I have for this one, only 4 or 8 bits are sent, okay, by this coding. The port number coding is shown here in this slide. You can send 4 bits by the last line or 8 bits by one of these, okay. And so this should have been 4 bits or 8 bits of the ports are sent if it is between these 2 numbers. All right. Sorry, so basically instead of putting all 14 bits, they put 1 or 2 bits which indicate, how much of that you don't have to, send on the wire. All right. That brings us to the end of this module, which is 6-LoWPAN. And the summary is as follows. And this you have to remember, that it introduces 3 new headers. Mesh addressing. Why? Because there are intermediate destinations. Hop by hop, so that you can do mesh broadcast. And destination address, so you can do fragmentation. And then we have, by the way, this is called destination processing. The fragmentation part is called destination processing because you can fragment at any point when you enter 15.6, but you don't reassemble when you get out of 15.6. You reassemble at the destination, which could be miles away. So if you made these little tiny packets for 15.6, when you get out and you go on Ethernet, you just have to pad them, big, so that they become big enough to travel Ethernet. And then at the destination, final destination, wherever that happens to be, you will reassemble it. Is that part clear? All right. So that's why it is part of the destination processing header. In IPv6, there are headers which are processed at every hop, which is like mesh broadcast, and there are headers which are processed only at the end. Okay. So this is like the reassembly. Fragmentation can be done at any hop, but the reassembly is done only at the destination. Then the address formation. So now you know that you can make 128-bit IPv6 addresses by prefixing with FE80. And then header compression. That there is header compression SC1, SC2, and then third one is called IPSC. And that compresses everything. And now I don't think I want you to remember the coding, but you have to remember that what are the things that can be compressed. So this is what I can remember and you should be able to remember. We can compress, so suppose I asked you, can you compress the addresses? Source address, destination address, source port number, destination port number, flow ID, ECN, DSCP. This much you should remember. Right? If you can't remember that, then you haven't done the study. So but whether the code 10 is this, 10 is that, 20 is that, don't worry about it. Understand? All right. Yeah.
So another question is that, so when the sender sends one of the fragmentation,
Yeah.
it could be the fragmentation could be lost, right?
Permutation?
Could be disappeared.
Yeah, some fragment could disappear.
So
Yeah.
how the sender notice that
Yeah.
fragmentation?
What will happen is, okay, so let's just answer the question. The question is, what happens if a fragment gets lost? Well, every fragment has an offset field. So when at the destination the puzzle is being assembled again, you will put everything as it comes, then you will see some gaps. Right? That packet cannot be used. And if it happens to be right on the same, well, actually it is already in the wrong layer, because remember 15.6 will retransmit it anyway if it gets lost and if it knows that it got lost, right? But if suppose it doesn't make it anyway, that point the only thing is to retransmit the whole elephant again.
So how would the sender know that?
Oh, that is basically TCP.
Because you told me like you're going to use.
No. See, thing is, if it is UDP, they say forget it, throw it away. No, don't care. If it is TCP will say sorry, we didn't get it. So that is fourth layer. Layer 4 will take care of it. The layer 3 will not do. IP doesn't do anything.
Oh, okay.
IP does do the reassembly part, but it doesn't do anything more than that. If the reassembly is unsuccessful, it just throws away the packet. At most it might tell, but I don't think it even tells layer 4 that I throw away your packet. It doesn't know who to tell, because if something is incomplete, it's just not possible to do anything with that packet.
The IP is sent over UDP, right? The IP.
No, UDP is sent over IP. Remember, layer 4 is sent into IP packets. IP packets are sent over 15.
Because you told me like the packet is over the UDP and UDP is out, right?
Okay, you are confusing. Okay, let me see what is over what. So basically, most of the information is some kind of meter reading. That is application data, right? And there is some kind of header which we'll talk about in the last lecture, actually, if we get to the last lecture, which I don't think we'll get to at this time. But if we get to the last lecture, then there is application data that is put inside UDP packets. Those UDP packets are given to IPv6 packets. Now those IPv6 packets have to be sent on 15.4. This is so we use 6LoWPAN because to send on IPv4 it will require a lot many more bits, so we cut down the bits as much as we can. So we use the compression. That's all there is. Layer 2, inside there is layer 3, inside there is layer 4, and so on and so forth. So it is not on UDP. The application is on UDP, UDP is on IP, IP is on.
So you need no virtualization, no overlay network.
So yeah, I think you're confused with that we talked about in the virtualization. Yeah, there is no virtualization. These are all pre-virtualization days actually. I think 6LoWPAN is not that new. Yeah.
When we think about the personal area network, I think about a small number of devices, and we have to shoehorn this IPv6 into another protocol just to get it working. Why don't we use IP4 with the fragment addressing instead of going through all these changes?
Yeah. I mean, so the thing is, okay, I mean, that's another point of view, and that's why IPv4 continues. It's just too complicated, and just too big, and too in all that, So the thing is, and this thing goes through the generations. There was a time when the bits were very expensive. Every single bit was squeezed out of the header. Then there was a time when the bits were cheap, and then we said no, everything should be, bits should be, header should be long, everything should be fixed place and all that. Then there is a time again, and there is a time again. So this changes by the year. Okay. So when IPv6 was designed, the bits were no problem. So All right. So I think we do 6LoWPAN now. So here is summary of 6LoWPAN. 6LoWPAN is all about compressing, making things small, fit into small boxes. Okay. Now we're going to go to another protocol, which I do want to finish today. And if I finish, then you got to read it yourself, because there is no Monday class. And that is RPL. RPL is routing protocol for low power and lossy networks. Now remember, this is low power and lossy. It looks very similar to 15.4, but it doesn't say wireless anywhere in the title, and it doesn't say 15.4 anywhere in the title. All right, and it doesn't say IPv6 anywhere in the title either. So this is a routing protocol. What is a routing protocol? This is different thing now. Just change your whole mindset. Routing protocol is OSPF. Remember OSPF? That makes a routing table. So how do you make a routing table for Internet of Things? You need the slides? They're right here. So basically, routing protocols are, so we are talking about how do you make a route on a small device network. And for that, the protocol is called RPL. So RPL competes with what? OSPF and a RIP and so on and so forth. So let's define something. Low power and lossy network is called LLN. And the route, even though they are called routers, but they are really tiny devices, and they cannot use OSPF, OLSR, RIP, AODV, DSR, etc. Now these are all the protocols that are used on the wireless and other places, but we can't use any of them. And if you don't know them, I have put the acronyms at the end. You can look them up on Wikipedia. The idea is that we cannot use them, but that's all. So LLN links have high loss rate, have low data rate, have instability, and therefore the bits are expensive, and the topology changes very fast. So we have dynamically created topology. Topology might change every minute or every few minutes. Now this covers both wired and wireless networks, and it is actually designed for meter reading originally. So basically you have lots of devices that you want to read sitting at one place. So it is really designed for N-to-1 communication. N-to-1 communication. Sync. Data sync. All the data comes into one place and goes there, that's it. Okay. However, you can do that 1 to n, the other way around, and you can do 1 to 1. This meter can talk to this meter if necessary. Generally, in the original application, it was not necessary. So they have made it possible, but it is expensive. This is very cheap. Going to the root is very cheap, but going anywhere else is expensive. All right? Yeah.
N is E or 1 is E?
N to 1. Okay, so the question is, what is 1?
Yeah.
Okay, it will come up in a minute. Okay, 1 is actually, it cannot be a meter, because I mean every meter, if it's done to a meter, what are they going to do? So it has to be something that is connected to the rest of the world. And so n to 1. Multiple LN instances on the same physical network. So you might have many instances on the same physical network. Okay, so you might have the same devices, same wireless thing, but there might be different places the information is going. So I'm going to introduce some concepts. First of all, DAG. DAG is directed acyclic graph. And directed acyclic means, directed means there are arrows. You see here arrows. And acyclic means there is no cycle, and it is a graph. So this is a DAG. Now, if you have destination-oriented DAG, that means there is one destination that everybody wants to get to. That means there is one route. Then it is called a DO-DAG. Destination-oriented directed acyclic graph. DO-DAG. If there are more than one route, then it is a DAG. If there is only one route, it is a DO-DAG. And when you say up, up is always going towards the root. So this link is up. Can you see that link? It looks like going down. But it's not going down, it's going up because you're going towards the root. Alright? And down is obviously going away from the root. And objective function, so basically how do you know whether you are close to the root or away? There is some function which the designer must have decided that, okay, I want latency to be minimized, I want energy to be minimized, I want whatever to be minimized. So that is not specified. Whatever you decide, by that function, you give it a number. You give a distance. And so that's how you figure out how far you are from the root. And you generally talk to the people who are closest to you, and then they send it over to the root. So the objective function is minimize energy, minimize latency. The rank is your distance from the root. So generally what you do is everything is just generally made integers. So whatever distance you have, let's say your power is 1.3 millijoules or whatever, right? You divide that by some unit, some minimum number, and you make it an integer. So that is your distance. So rank, that is your rank. Then RPL instance is one or more DO-DAGs. So this is one RPL instance. It has two DO-DAGs. One DO-DAG which has this root, and one DO-DAG which has this root. So a node may belong to multiple RPL instances, and you could have one more RPL instance, and the same node could belong to that one too, because that is being managed by more than one people, whatever. All right. So DO-DAG. DO-DAG ID. Each DO-DAG has an ID which is basically the IPv6 address of the root. So it has 128-bit ID. As long as the root doesn't change, the ID doesn't change. DO-DAG version. Every time the DO-DAG changes its shape, it's a new version. Right now, this is the version, and 5 minutes later, the root is same, but the shape has changed, so that's a new version. So the version is changed from 5 to 6 to 7. So the root keeps track of that number. And in all the announcement, it says, look, I am using version number 5. If somebody has the old information, version number 4, they have to update right away. DO-DAG version number. Current version of the DO-DAG. Every time a new DO-DAG is computed, the same root, the version is incremented. All right, everything is clear on this slide?
So for one-to-one, that is why for one-to-one communication, a lot of work would need to be done.
Yeah, because this is all designed for the root. All right, goal. Now we talk about objective function. Objective function is energy and latency. Goal is where you want to go. All right. Generally, most people want to go to some wired network. And so that is your goal. Your goal is to get onto the wire from wireless, or from this little electrical wiring to internet. That's your goal. Right? So goal is different. Don't confuse goal with the objective function. This will be clearly in the exam, right? Very easy to ask. Goal is latency? No. Goal is where you want to go. Objective function is what you want to minimize. Alright? Now, if you can reach the goal, it is called grounded. So this DODAG is grounded because it is connected. If it is not connected to the goal, you cannot reach the goal, then it is called floating. I am still looking for the destination. I can't reach there. Then parent. Obviously parent is where your arrow goes and child is where the arrow comes from. So each parent may have multiple childs. And you may have multiple parents as well. Okay? And then generally the parents will not be in the same DODAG. You might have a parent in this DODAG and another parent in another DODAG, so that there is no cycles of any kind, right? Something like that. Parent, sub-DODAG is sub-tree. Actually, sub-tree is a misnomer because trees don't have direction. But if you just take the thing underneath you, that is your sub-DODAG. Alright? And then there are two kinds of nodes. Some nodes keep the whole routing table and they know how to go from A to B. Some nodes are very simple, they don't keep any routing table. All they know is who is their parent. They are like children, you know, the little children, and then some adult children, right? So little children, all they know is their dad and mom, and that's it, nothing more. And so whenever you give a packet, they give it to their parent. And the parents give it to their parents. The whole, by the way, whole DODAG has to be non-storing or storing. So basically it will come in a minute. So even though you might be, is adult enough to be remembering the whole table, if you are part of a DODAG where everybody is non-storing, you have to be non-storing. Okay? Except for the root. Root is the only one which has a little bit of smartness, and it is always storing. Alright? So the rest of the network, so the whole DODAG is either storing or non-storing, depending upon whether everybody keeps a routing table. If they don't keep the routing table, they just need to know who their parent is. So there are 4 messages which are designed, or 5 messages which are designed to find out, to form this table. Actually, all we are doing is spanning tree in some sense, right? So there are 4 messages. First is DODAG information object, which is the downward multicast. So which says that, which is like a beacon, which says, look, I am part of this DODAG and it is grounded and we are all storing. If anybody wants to join, please let me know. That's a DIO. Now, the thing is, beacon is coming from only from the access point. Okay. Beacon is coming from the access point. In this case, DIO is coming from all the leaves. And from the access point as well, actually. It is coming from everybody. Everybody is saying that I am part of this DIO, I am part of this DODAG. If you want to reach Germany, here is the DODAG, and it is grounded right now, it's connected. So, and if you don't hear any announcement, then you can send a request which is called DIS. DIS is just, is there any DODAG here? I want to go to Germany, like that, DIS. And DAO is the object, which is actually a request which says, can I please join your family? Can I join you? That is DAO. And then DOAAC, the answer to that DAO, which says, well, sorry you cannot join, I'm already overloaded, or sorry you cannot join because, this, whatever reason. So that ACK is called yes or no. And consistency check has to do with the security, which we will not discuss. So anyway, so generally a new guy will come in, will send a DIS, it will get a DIO from somebody, and then it will say DAO, and then it will get DOAAC. So is there anybody here? Then they say, yeah, we are here, and this is the thing, and they say, can I join you? And then they say, yeah, you can join. Clear? It is quite possible that you don't have to send DIS, because if you wait long enough, you will find a DIO, and then you can do only 3 steps. 4 messages. This you got to remember, right? Clear? All right. So now let us give you an example. There are 5 nodes, and they have no connections, no DAG, nothing like that. So the first one says, look, I am the root. And by the way, root is programmed beforehand. Because not everybody can be a root. Everybody is not connected to the ground, and so on and so forth. So some nodes have capacity to become root, and they're programmed like that. So they will say, oh, I have a DAG, and this is the DAG ID, and whatever, right? All of these guys will listen to it, and they will find their distances, and all of them will actually try to join. Regardless of the distance, they will try to join. Because that is the minimum distance right now for them. And so all of them will send their request DAO, and they might even join it. But in the next round, what will happen is when they hear the DIOs from B and C, they will find I'm closer to B than A. So they will say, no, I don't want to go and join that guy over there. It's very far. The rank here is much lower if I join here. So then D will join B, and so on and so forth. So they will disconnect from A and connect to nearest neighbor. So that is what the process is basically. The process is listed here. B, C, D, E here, and they join. And then they send a DAO. They're not all shown, but basically they send a DAO, and it accepts. Then B and C multi-class DIOs, and D hears them, and it knows that I am so much distance. D says that I am distance 1 from B and distance 2 from C. It says to B, can I be your child, please? And then B says yes. So at the end, this is the DAG which is found.
So number 4 is A accepts only B and C, right?
A accepts all, huh?
It's not all, because D.
Okay, so here's the thing. There is a slight difference in the picture shown here. So the picture says that everybody hears, but picture says only 2 people send the DAO. Actually, I have to change it. So everybody sends the DAO, and everybody gets the DAO. So at that point, the picture would look just a tree. With one, everybody connected to A. No, makes sense. So you connect to whatever right now currently is the minimum. Currently, if you have nobody else to join, you just connect to A. But a minute later, when B announces, then you figure out that B is, if I go through B, then I'm at a distance of 2, because B says I'm at a distance of 1 if anybody wants to join, and this one says I'm at a distance of 3 or 4 or whatever, right? And if I go through B, it will be less. Then you change.
So D can release the connection.
B can?
D release the connection between the...
Yeah, D will release the connection from A and connect to B. Similarly, E will release the connection from A and connect to C. Okay? Yeah.
I have a quick question about number 5. Since these are DAGs, is there a difference between the dotted arrows and the straight ones? Because it looks like 5 has some...
Yeah, right. Yeah, there's a difference between dotted arrow and the fixed one. The dotted arrows are messages. The fixed ones are connections, are associations. So this is now B is a child of A, C is a child of A. This one is not a child. This is just a message going. This is complete DAG here. So the D is a child of B, B is a child of A, like that. All right, now data forwarding. So now if you want to send from N to 1, basically you change it, set the address and it give it to your parent, and the parent gives to their parent, it will go to the root, no problem, right? Now if you want to send from A to B, how do you do? There are 2 cases, storing and non-storing. If you store, then you just say, okay, who is my common parent? If I want to go from A to B, and you know the whole table, you know who is the common parent, you send it to the common parent and go down from there. If you're non-storing, you don't know anything about who is where, all you do is you give it to the root, and the root knows where it is. Right? So everybody sends it to the root, and then the root puts the whole source route, says, okay, it will go to here, 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 and it will go to B that way. All right? And then you want to broadcast from the root. That's very easy. Broadcast from the root actually, if it is storing, then everybody knows who to give, who their children are. If it is non-storing, then you don't know who your children are. Can you believe that? You only know your parents, but you don't know your children. So Basically, the root has to tell you who your children are, and then you can send it to them, and they can send to them, and so on and so forth. All right, so that is non-storing. That brings us to the end of RPL. RPL is the routing protocol, just like OSPF, which is used for these simple devices, and all it does is forms a kind of a spanning tree. And by forming the spanning tree, actually it is much simpler than a spanning tree, but basically that's what it does, and then everything goes to the root, and then you don't have to remember any routing table. All right, that brings to the end of this module, and we talk about two different protocols, 6LoWPAN and RPL. They are not competing, they are different. RPL is the routing protocol, and 6LoWPAN is a compression protocol. The main thing about 6LoWPAN is how to compress, how to make things smaller. So basically it's an adaptation protocol, and RPL is designed to find the route.